Alright, so does anybody have a problem that they would like to go over? That is of course what we do here. So I hope somebody has some.
The surface area of the torus, he went over it yesterday, but it just didn't click when he did it.
Well, surface area of a torus. Well, yeah. So first of all, you're going to need a equation of a, or like a how do I do this? There we go. The surface area of a torus, huh?
And what the radius was to the center of the torus, as far as the center of the interior, and then the little r was the radius of the circle as the cross section.
Right. So yeah, so there's this torus, right? So it goes around like this, and it's got a little radius that way, and then it also, of course, goes this way. It's got like a big radius, like a donut shape, right?
Yeah. The homework had the big R going to the center of that, from the center of the torus to the
Oh,
center.
sure. That's actually a much better way to define it. Yeah. So to there.
Yes.
There you are. Okay, cool. So how do you find the surface area of an object like that? So you need to come up with a way of expressing that as a solid of revolution, right? Which it totally is. Right. One great way of doing it would probably be to put it on. There's lots of ways. There's lots of choices. One way would probably be to put it on an axis like this. And so just think of it as it's this circle that's been rotated around the axis, right? So does everybody see how if you take that circle and you were to rotate it around the central thing, it would make the whole torus? So yeah, so if we look at it that way, then we should be able to find the total surface area. Now I low-key got to remind myself so is it just well no, you're finding the surface area. Yeah, I might have to remind oh no, I remember, isn't it this one? Isn't it so if you've got a function that goes like this or whatever, and you're rotating that whole thing, so each of these things rotates around like this, right? And the whole thing rotates around like that. Is the surface area, and let's say this is from, let's say 0 to b, is the surface area?
That would be 2 pi.
Is it that, or am I thinking of something totally stupid? Low-key might have to look it up. How embarrassing. No, it is the other one, isn't it?
I thought it was 2 pi f of x times the r way.
Yeah, it's that one. I'm thinking of something totally not relevant here. Yeah, so it's the sum of all the circumferences, right, with respect to the arc length, is one way you can think of it. So then you can just pull those out, and then this is the thing that's changing, and then this wacky thing is that, right? And then if that's not, if there's something like that. Does that seem right? Everybody on the same page? Making sure I know what I'm talking about. All right. So all we got to do is come up with a description for this this curve, right? Now, so let me erase this whole thing so that it's a bit less distracting. So, but still, I kind of like red for the axes actually. So here we are.
Actually, real quick, when it's around the y-axis, it's x instead of f of x, right? Over on the right.
That's exactly right. And the reason is, and I should be thinking about this and I'm not, is because we're taking, okay, so let me draw it out first. So here's the curve that we're rotating around the y-axis, right? So we're taking this entire curve, and for every single one of these x-coordinates, like this x-coordinate, for example, we're taking that point on the circle, and we're rotating it all the way around. And so then that little circle is just one of the circles around the the full torus there, and then all of them together. If you do that with all of them, it draws out the full torus, right? So just one of these. Again, I'm used to having a back button, so I always do that. So all we need to do is just find the circumference of one of those circles, which would be 2 pi times the current radius, which is just whatever our current x-coordinate is. And then we just want to add all of those circumferences together, all the way from here to here. So I absolutely should have known that it's 2 pi x, because the radius of this circle is the x-coordinate. It's this distance. It's not the y-coordinate, which would be f of x. That would certainly be appropriate if we were rotating around like this, but we're not. Okay. So yeah, so that's what we're adding up all together. The only tricky part is the ds, which is still going to be 1 plus the derivative of your function squared, right? So we'll have to find the derivative of this function, but before we can even do that, we'll have to describe the function. So we need some kind of function whose output is this circle. Now already you should think that's a problem, because this circle does not pass the vertical line test. This is not the graph of any function. There is no function which you input a certain x value and it spits out 2 different y values at the same time. That's not what a function does. A function can only spit out 1. So no problem. All we'll do is we'll just consider the top half of this bagel instead, right? So just only from there to there, and then that's what gets rotated around. And we'll calculate the surface area of that, and naturally the surface area of the full torus will be double whatever we get, right? The reason for doing that is because now we can express this curve as a function. Let's just say, for the temporary sake of argument, that this outer radius, right? We were calling it capital R, but for now let's just call it. Let's say it's 5. And then this inner radius, right, we were calling it little r, but let's just say for the sake of argument that it's 2. So can anybody tell me, what is the equation of this curve? It's a circle centered at 5, or so rather it's a semicircle centered at 5 with a radius of 2. Does anybody know the equation for that?
X minus 5.
Length of the circle.
Sorry?
Is it the length of the circle?
It is not the length of the circle. At the moment, by the way, we're trying to find the surface area of this shape. That's ass. Wait, that's not how you do it. Oh, it's torus. Toruses are hard to draw, for me, anyway. Something like that, like a donut shape, right? So we're trying to find the total surface area of that. So the length of each curve. I'm sorry, maybe I didn't understand what you were getting at. We're not trying to find the length of the circle. We can do that with geometry, no problem, right? We're trying to find the total length of all of these blue circles. So this one on the inside, all the way around to the very outermost one on the outside. The total length of all of those blue circles, which is exactly what we're adding up here, right? The length of each circle times the total length there. Okay, so go ahead. What was that again?
X minus 5 y squared plus y squared equals 4.
That's right. So does everybody agree that this is the graph of a circle centered at 0, 5 of radius 2? right? That should be familiar to everybody from who knows when. So that's great and everything, but that's not quite the format we need. We need it as a function of x. We need it as y equals a function of x. So no problem, we'll simply solve this equation for y. Right, so let's take this, put this over there. Yeah. And then square root both sides. Don't forget to add your plus or minus. Well, the thing about the plus or minus is it splits it into two different things, right? It splits it into y equals, it splits it into two curves now. Y equals the square root of 4 minus x minus 5 squared, which I can tell you looks like the one that we want. But then there's also the other one. Y equals the negative square root of 4 minus x minus 5 squared. And that's this one. And together, they make the full original circle. Right? So the full circle is captured by this equation, which is symmetric in x and y. But once you solve for y, if you want to write it as strictly a function of x, you have to choose either plus or minus, and that gets you either the top function or the bottom function. And so we could have chose either, but I'm going to go with the top one. Right? So there we have it. It turns out that our function is the square root of 4 minus x minus 5 squared. So that's our function here. So remember, we're getting this to try and fill in this formula, right? So this is no problem. The only part that's tricky is this part. So actually, we'll have to figure that out. So if f is the square root of 4 minus x minus 5 squared, and personally, I'm kind of a fan of using fractional exponents instead of radicals, because it's just better, in my opinion. Take the derivative, because it's easy to see how the derivative goes, right? Simple power rule, no problem. 1/2 times 4 minus x minus 5 squared to the negative 1/2, right? But don't forget about the chain rule, right? If this was just x, then that would be it, but it's not. It's this other function, so we'll have to take the derivative of that. Well, so 4 goes to 0, and then negative x minus 5 squared. So no problem. So that's just negative 2x minus 5. And maybe I should be clear. It's like that. Right? And the fact that minus 5 is in there is not going to matter, because, yeah, you could say do the chain rule again, but that's just going to be times 1. So you don't have to worry about that minus 5 messing up. If you want to, you can rewrite this. This is nice. This 2 and this 2 cancel each other out. I love that. And so you get negative 1. Oh, no, sorry. You get negative x minus 5 over this square root, right? So it's negative 1/2. So that's a square root in the denominator. Okay, so that's everything we need. We are finally ready to go here. We can actually do the integral. Oh yeah, but hang on. Problem is, I made up 2 and 5, didn't I? Right? This was supposed to be little r and capital R. So let me replace those real quick. That's going to be little r, and that's going to be capital R. So with those changes, can you see how you can still work out the equation of the circle? And you can still solve it for y, and you can still pop it into here, and you can still take the derivative. So let's just carry through for ourselves. How is this all gonna be different, right? Well, this is going to be capital R, and this is going to be little r squared, right? And so then you work this out, and so it's r squared minus this, etc. all the way through. So if we just carry that through, be careful here. So this is r squared, this is capital R. This 1/2 is still 1/2. This is r squared, this is still capital R. That's all good. And then this was, from here, negative 2x minus r. So in the end, this is what it looks like, right? This is x minus r, and then this is an r squared, right? So we can do it all again, but keeping the two things as variables. That way, instead of talking about a particular torus, we are managing to talk about all toruses at once, right? So that's the benefit of bothering to keep things in variables, right? So we're talking about literally all possible toruses all at the same time, right? So yeah. Okay, so anyway, so here we go. Plugging it into this formula. Can anybody tell me what are the bounds for x? So the bounds of where we're doing our integral with respect to x. So in the direction left to right, where does our curve start and where does our curve end? And before you might have said oh well 3 and 7, but now it's variables, right? So can anybody tell me what's the x coordinate of this point right here?
R minus r.
Yeah, that's right. Right, it's big R and then minus R. And then for the same reason, this is going to be big R plus R, right? So those are the two bounds. So those are the two bounds. So this way. So it's little r. Yeah, so it's there to there. The 2 pi we can pull out. The x can just go there. And then finally, it's that. So this thing called ds, right? We've got this little funny thing called ds, which is equal to this. If we had more time together, I would love to talk more about that and what it means. That's not supposed to be over that. And what it means, like geometrically and philosophically and stuff. But unfortunately, that's not really my role. So it's just this little thing that makes the formula shorter. And you replace it with that when you need to. So that's what we need to do. So 1 plus f prime squared. There's f prime. We've already got it. It's negative x minus r over the square root of r squared minus x minus r squared. Everybody on the same page with that? Right, so that's 1 plus f prime squared. And so we work this out. It's going to be 2 pi times the integral. Well, this, I hope you can see, has tremendous potential to be simplified, right? Because the square can distribute over in the numerator and denominator. And so in the numerator, the negative gets squared, so that doesn't matter. This other thing gets squared. And this square root gets squared, so that's just gone. Gotta love that. Gotta love that. Okay, so low key, let's actually do this on the side, because I feel like there's
Just so you know, this is the path I went down.
huh?
And I got lost somewhere. When I asked him yesterday, he did it completely different by just taking 2 short equal lines off of the center, and I appreciate it this way, because this is the way I was doing it as well. So
Do you have the way that he's doing?
I have a picture of it.
I'd love to understand. So let's see if we can simplify this more. Right. This is 1 plus x minus r squared over r squared plus x minus r squared. I suspect that you can simplify this if you give these the same denominator, right? This 1, a really ridiculous but useful name for 1, is r squared plus x minus r squared over r squared plus x minus r squared. And that's super useful to us because that's exactly what we have to add it to. And it's super useful for us because now when we do, oh no, I was wrong. Wait, no, it's minus, isn't it? Sorry, these denominators are minus. So that's super useful for us because now when we add these fractions together, this 1 plus this other guy, well, these actually cancel out. So they combine to be a single fraction of the very nice Right, so that's kind of cool. And then we're taking the square root of that, and then multiplying that by x. Oh my goodness. So this would become x times the square root of r squared over this. And then finally, I'll distribute that square root. So that on top it cancels there. And then the bottom we get that. Right, so this r is a constant, so I can pull that out. And this x, I might as well put that up there. Yeah. Okay. Sorry. Do you have that? I'd love to see just what you're turning right to. Oh, okay. Yeah, that's another way one could do it. Holy crap! Wait a second. dA is. So he's doing them as functions. Sorry, I don't understand what he's doing.
Wish I could explain it.
Yeah, that's okay.
I couldn't either.
Well, me too. He's got like 3 radii.
He was giving him his own designation. so-
Sorry, I don't know what he's
That's
talking about.
Yeah.
Yeah, so this is the way that makes sense to me, right? Because we're going, you know, over the semicircle, just each one of these, wrapping it around, and then adding those all together, right? Yeah. Okay, so does anybody know how to do that antiderivative now?
Real quick, can you go over that again?
Sure. Which part?
Just
What is
the
it?
just the part of like that part in the corner.
This part here.
Yeah.
Yeah, sure. So we were at this stage where we have to simplify, you know, 1 plus, this was, you know, 1 plus f prime squared, right? And I was like, okay, I bet you there's a bunch of algebra that will make that nicer, and I'd rather not write all this extra crap every time. So let me just do that over on the side here. That stuff that's inside the square root, the 1 plus f prime of x squared, well, we already worked that out, right? You know, f prime of x was this, so when you square it, it becomes this, right? But this is 2 separate terms, right? Which is problematic when we want to simplify with the square root. There's not really anything you can do to simplify a square root of 2 separate terms like that. So I'd love to combine those together into a single term, and it turns out it works really well because, well, you can see that this 1, you know, in order to combine these into a single term, we have to make them fractions with the same denominator. And so this one I'll leave the same, and then I'll give this one that denominator, right? This is the same as 1,
Oh, okay.
right? That's a valid move, is I'll just rename this 1 as this ridiculous thing, so that they have the same denominator. And then now, gorgeous, the negative x minus r squared and the positive x minus r squared cancel each other out. It becomes this super nice thing down there. So yeah, so these 2 terms actually can be combined together into this single term. And the way it worked out is actually pretty nice, especially because the numerator is a perfect square. Because the next thing we got to do, remember this whole thing was this, right? And it's inside the square root. So once we simplify that, then we can actually take the square root. I kind of did that real quick. Let me honestly split that up. We can honestly take the square root. So, and upon doing so, in the numerator, this r squared square root is just r. So it just gains an r on the outside. Still has an x here. Sorry. And then the numerator has nothing left. Well, the numerator, I'll just give it the x, I guess. And then the denominator has the square root of r squared minus x minus r. Does that make sense?
Yeah, it does. Thank you.
All right. Ooh, okay, so at this point, does anybody see? I feel like we're at a point where we can pretty much solve this integral with one substitution. Does anybody have a suggestion? It's one substitution away from being a nice little power rule. Believe it or not, remember that capital R and little r are just numbers, so in your mind, consider them like 2 or 7 or whatever. So, yeah. So how would you go about solving this integral? You know, x over the square root of 5 minus, x minus 2 squared.
U sub and du is minus 2x.
Yeah, something like that. So yeah, what would you recommend for our substitution?
I get the minus x minus r squared. Take the whole thing. Or I guess you could take the whole interior.
You could even take the whole interior. In fact, I would strongly recommend that. That's not really going to change the derivative, right? And the derivative would end up being what? Well, it would end up being Well, it would end up being x minus r. Well, so that's okay. So there's negative 2x minus r, which is kind of unfortunate, dx, because that's not quite the numerator, but that's okay. We can make that work. Let's see. Man, that really kind of screws it up, actually.
Perhaps the difference of squares there.
It sure is. So if we wanted to, we could rewrite that denominator, right? Right now it's a squared minus b squared. And I'm sure it's familiar to you that that can always be rewritten like this. So it might be a useful trick that we could rewrite this denominator instead of the square root of a squared minus b squared. We could rewrite it as the square root of a plus b times a minus b. But I'm not sure that is any help, right? Because now it's just kind of, yeah. Okay, so we'll have to deal with that. Hang on, let me just make sure I'm not going totally off the rails here. I'm scared now. Somehow I screwed it up somewhere. I think so. Something. How would you? I'm finding the same diagram, but that's not really. So
That's not the inverse sine.
yeah, so what we can do, we need this to be x minus r, right? So here's what you can do. Give it one of those, right? Because you can say, yeah,
I have
yes.
a question. What happened to the r squared in the u when you take the derivative?
Well, great question. So remember that r squared and little r and capital R are just numbers,
Okay.
right? There's some number, and we're leaving them as variables so that we can plug them in later. But in this context, they're just some number. So imagine that was like 2, you know? If this was like u equals 4 minus, like it was before, u equals 4 minus x minus 5 squared. Well, when you take the derivative of 4 is 0. So it's just gone, right? This whole term goes away because it's just some number,
Gotcha.
right? And then this term is the one that's actually the derivative, right? So you can take the power rule and then you look at that, right? So we need this exponential r. Unfortunately, it looks like we're going to have to split it up, which really is unfortunate. And I wonder if I've gone astray, almost. I hope I haven't made a mistake so far. But I think we're going to have to split this up, right, as two separate integrals, right? So 2 pi r times, so we've got one integral of x minus r over r squared minus x minus r squared dx plus this second integral, which is just r. So might as well even pull that out. It's just r over just that, right? So this one we can hit with the substitution. The one that we said down here, we needed to have a -2. Well, you guys, I think I like to do it a different way, but you guys, I think, like to do it this way. Right, if you have something like that with a coefficient that you don't have, you simply divide it over there instead. All right, that's a great way to do it. So yeah, so I'll just do that to that one. So this is u. Oh no, sorry. This is -1/2 du, and this is the square root of u. So that's great. I'm going to leave my bounds in x. When you do a u substitution, you're welcome to take your bounds with you. I personally find it easier to just go back to my old variable when I'm done. So this is all du. And so this is literally just 1 over the square root of u du. Great. It's a parentheses. Plus this one. So does anybody know that?
Did you get your 1/2 in front of that one or no? You multiplied by 2 earlier?
You totally right, thank you. -1/2 du. What is that, like arc sine or something?
Yeah.
R 1 over that? Does anybody know? On the same page with arc sine? Minus.
Oh, there's not a 1 over 8 in front. There's just for arctan.
Really? Why is it so hard to find?
Or I just arc sine of x over a.
Sure. I'm just struggling. I normally can pull up the whole. Here it is. Oh yeah, look at that. So 10 and the other one have that on it, but that one doesn't. Kind of funky.
Neither I can.
Okay, so great. So that means we don't have that. Okay. Something doesn't look right.
Wait, do you want to see this explanation I found online?
Sure, I think I might have made a mistake somewhere.
I don't know how to interpret this.
Okay, sure. So, so they're doing it a completely different way. They're doing it with polar coordinates. Yeah, so they're doing it a completely different way.
I still don't understand.
So there's not really much to say about that. Yeah, so sorry guys, I think I must have screwed up somewhere because this doesn't seem right. Well, this is definitely not right. This term is definitely not right because
Would that be x minus r over r?
yes. Okay, never mind then. Never mind then. Okay, so let's do this.
I think that's all going to disappear, isn't it?
Yeah, you might be right. You might be right. Where can the camera see the last word? Sure can. Oh, not very well though. I think we better move back over to the left side. Okay. All right. Yeah. Okay. So keep on with that. So that's what's that? So that's u to the negative 1/2, isn't it? So u to the negative 1/2. If you bring that up, it would be u to the positive 1/2. So that means it's the square root of u. It's that, isn't it?
Yep.
Right. 1 over the square root of u would have to be that because only then would the power be negative. Would be 1/2 negative 1. That's right. So great, so that cancels with that negative 1/2, and it's just negative. So it turns out we get negative square root of u from here to here. Right? Am I doing this right? Negative square root of u from there to there, and then this from there to there. Right. So it's 2 pi r times okay. So here, unfortunately, we have it as square root of u, but remember that u was equal to this r squared minus x minus r squared. So yeah, so we can fill that in if we want. So this is negative square root of u, which is r squared minus x minus r squared. And so now check it out. When we plug this stuff in, it's gonna go great. Because when we plug in this top one, plug in the top one, this is going to be r plus r minus r. So that's just going to be little r. So it's right. So can everybody see how this is going to simplify down? This r on the inside is going to cancel with that r, and so you're just going to get positive r. So you're going to get r squared minus r squared. So you're just going to get 0, and then it's going to be the square root of that, and then it's just going to be the negative of that. So it's just 0. And isn't the same thing going to happen here? Because you get, instead of positive r squared, you get negative r squared, and so the same thing's going to happen. Okay? So that term goes to 0. This whole integral, that whole first thing goes to 0. Okay? Let's take a look at the second one. This one. You plug in the same thing. The big R cancels, and you get R over R. So you get arc sine of 1. Interesting. And then minus the little one. So you get R times arc sine of. Well, if you plug in this one, again the capital R's cancel, but you still have a negative little r over r. So that's negative 1. So, and then it's 2 pi r times that whole thing. So it's 2 pi r times this difference, right? So can anybody tell me what is the arc sine of 1 and the arc sine of negative 1? Arc sine of 1.
Or no pi over 2?
That's right. For arc sine of 1, you're asking where on the unit circle is the sine 1? Where on the unit circle is the y-coordinate equal to 1? And that only happens right here. Right there is where the y-coordinate is equal to 1, and that angle is pi over 2. So sine of pi over 2 is 1. So in other words, arc sine of pi over 2, sorry, arc sine of 1 is pi over 2. How about negative 1? Well, same deal here. It only happens there, which is only at the angle negative pi over 2. So that's r times negative pi over 2. And so the way these end up simplifying, right, is that's, damn, we're off by 2.
That's right. It's our,
Well, the way these end up,
it'd be a plus r times. That's r times negative pi over 2, right? So it's a positive.
yeah. So then together that's just r times pi, so we get 2 times pi times r times capital R times pi again. So in the end, we've gotten 2 pi little r capital R. And unfortunately, the correct answer is 4 pi. 4.
Is it just the top half?
You got 2 pi squared r, and the correct answer is 2. But fortunately, at the very beginning, we cut it in half, didn't we? So boom. So the actual torus is
Wow.
4 pi squared. Pi squared. Right. There you go. So we got it. All right. So yeah. So that was very long-winded. I will admit. But the power of it is that now you have produced from nothing. Like all you knew about the torus was its geometry, and then you knew how to convert that to algebra, and then you knew how to perform calculus on that. And so you have done something that the ancient geometry people that you learn about sometimes could only dream of. That you have found the amount of area on a curved surface, and not just one, but all of them, all at the same time. You've now found a surface area formula for all tori that are possible. You've got it, right? You just multiply the 2 radii together, and then multiply by 4, and then multiply by pi twice. And that's the surface area of the torus, yes.
So now, if we ever see one of these again,
Yes.
can we theoretically, since we've done it all this in class, can we just say, oh yeah, I remember that, I'm just going to write that down?
Well, great question. If you're in real life and you need to find the surface area of a real life torus, and you can be like, boom, there you go. That's the answer. But unfortunately, sometimes when you're in school, it's like, I know you might have seen this before, but I'm testing you on your ability to do the whole thing again. So you're gonna have to do it all again. So it just depends. You'd have to ask the teacher, but probably if it's like on an exam, then we're probably supposed to go do the whole thing again, which kind of defeats the purpose of it, honestly. Yes?
What happens to that negative half that's on the right side of the bowl?
Right here.
Up a little bit?
Right here.
Yes.
Man, sorry, I kind of skipped too many steps.
Yeah, I think that's 2.
It came from here, right, yes. So this integral here, this was negative 1 half times the integral of 1 over the square root of u. Well, the integral of 1 over the square root of u is 2 square root of u. So, and then from here to here. So these 2's cancel. Right? These 2's cancel, and you're left with only negative square root of u. And so that's why the next line was just negative
Gotcha.
square root of u.
For you.
And those
So that
2's had
u is
gone away.
equal- Okay. That
Right,
makes
so
sense.
so the 2's cancel each other, but it leaves the legacy of the negative sign. Right. Yeah. Man, so it turns out I didn't make a mistake the whole time. Man. Great. It's really easy to screw these up because they can be so complicated with all the variables. Man. All right. So sorry, we kind of spent the whole class on one problem.
Good problem. Good problem.
Are there any other problems that you might like to go over if you would like to stay a little bit longer? Otherwise, you're welcome to go. Actually, hang on. Can I do a show of hands of whether you would like to continue to do these in person or just do them entirely online? In person. Wow, and online. Got it. Okay, thank you for your feedback. I will take into account that is of the people who choose to come, so that's a biased sample, right? So.
It is a bias sample.
Yeah. Okay. All right. Thank you for coming, everybody. If you want to stay another 15, you can, and I'll do another problem. But go ahead and leave. Have a good one.
Thank you.
Thank you.